Hello, this video is about completing the square, which is a handy technique for manipulating quadratic equations and solving them without factoring, at least without the normal kind of factoring. It's more based on recognition. So the idea is completing a perfect square trinomial allows us to factor by noticing something as a square. That's very vague right now. Let's look at an example. Suppose we wish to solve this equation. Now, based upon what we were talking about in the previous section, we would set this equal to 0, and that's fine. But what we might notice is that this thing here factors as x minus 3 times x minus 3, which means it's actually a perfect square. It's the result of squaring something. And if we have something as the result of squaring, it's easier to think about what's going on. What we actually have here is that x minus 3 squared is equal to 25. And especially with a number like 25 here, you might think, oh, yeah, 25 is the result of squaring something. It's the result of squaring 5. But let's be very careful. Or there's actually another number where if we square it, we get 25, and that's negative 5. So I do want to warn you here. We need to remember that plus minus. Just because it instantly occurs to you that 5 squared is 25, that doesn't mean it's the only one. But what we've done here is similar to what we saw in the previous section. We've taken what was originally one complicated equation, and we've swapped it out for two easy equations. The solution to the first one would be x equals 8. The solution to the second one would be x equals negative 2. And for either one of those, you could plug it in to check that it works. So by noticing we had a perfect square, we didn't really have to factor. We just had to use that observation. So now, let's tweak this a little bit. What if we had this? X squared minus 6 equals 91. So this is not a perfect square. But what we see, especially with this previous example in mind, is that it's very similar to a perfect square. X squared minus 6x plus 9 is a perfect square. So it's almost a perfect square, but it's missing a plus 9 at the end. Well, we can manipulate this equation. We're allowed to add that 9 as long as we add it to both sides of the equation. We're noticing in that previous example, having a perfect square made things really nice. Let's create a perfect square. So I do that by adding 9 to each side. So what we have on the left, as before, is quantity x minus 3 squared. And on the right, very conveniently, we might notice we get 100. So this means that x minus 3 is equal to 10, or x minus 3 is equal to negative 10. So our solutions would be 13 and negative 7. And you can check that they work by plugging them in. So what we did here is we took something that was not a perfect square, but created a perfect square. That method is called completing the square. We have something that is like a perfect square. It's like this perfect square, but incomplete. And we did exactly what we needed to turn it into a perfect square. We completed that trinomial, 1, 2, 3 terms, perfect square. So in order to get completing a square, we want to notice patterns. So hit pause and actually FOIL out all of these. Okay, I hope you've done that. So this first one works out to x squared minus 2x plus 1. The second one works out to x squared plus 14x plus 49, x squared minus 8x plus 16, x squared plus 20x plus 100, and x squared plus 12x plus 36. So let's notice the pattern here. Let's look at this second number. Let's look at this coefficient of x in the expanded FOILed out version. And let's look at this constant at the end. What we will notice is that this middle number, the coefficient of x, is always double what we see here. -1 to -2, -4 to -8. 10 to 20. The number at the end is always the square of what we saw at the end. So if we notice this pattern, we can actually think, how can we get something to be like a perfect square? So for example, if I had x squared plus 16x, right, working backwards, we might think, oh, to get a 16 here, it means we had an 8 there. And if we have an 8 here, we'd have 8 squared, which is 64 here. So if I started with x squared plus 16x, I sort of know how to complete that to look like this pattern. What we essentially did is we looked at this number, 16. We asked, what's half of that to figure out what goes here? And then what is that squared to figure out what goes here? So where that 16 actually came from is where the 64 came from, we took 16 over 2 to get our 8, and then we squared it. That's where that came from. So this is what that concept is, presented somewhat abstractly. Whatever coefficient we have here, assuming we're starting with x squared, you take half of it and square it, and you add that on. So I'll do one example, and then you can pause to try the rest. So here, we have x squared plus 6x. So if we take half of the 6, we get 3, and 3 squared is 9. So if we add 9 here, we get x plus 3 squared. So hit pause and try to figure out in each case, what could you add to create a perfect square, and which perfect square do you have? Okay, I hope you've done that. Here, half of negative 14 is negative 7. If we square that, we get 49. And we have x minus 7 squared. Here, 8. Half of 8 is 4. 4 squared is 16. And what we have is t plus 4 squared. Here, half of 3 is 3 halves. And 3 halves squared, I'll just do a little work on the outside, is 9/4. If you have an odd number, it's not so pretty. But what we have here is quantity y plus 3 halves squared. It still works mathematically, even though it's not as elegant. So now we can use this to solve equations. So let me just do an example while you watch, and then I will walk you through the steps. So I will add a page here. Ah, that's from a YouTube video. Let's try that again. Okay. So let's suppose we want to solve this equation by completing the square. So right away, something you want to notice, we just want to hit the brakes. If you see anything besides plain old x squared, you want to get rid of that. The technique we have here only works when we're starting with plain old x squared or y squared or t squared. So right off the bat, I can divide everything by 2 to fix that. So I have x squared plus 6x minus, not minus 4, I'm dividing everything by 2. Minus 2 is equal to 0. Now also, I want to just see a binomial. So I'm going to move the 2 to the other side. Okay, so now I'm going to use completing the square. Here I have something that is presumably 2/3 of the way to a perfect square. Following the technique before, half of 6 is 3, 3 squared is 9. So let's add 9. So I'm going to write it like this, x squared plus 6x, and in a different color, plus 9. Well, whatever I do to the left-hand side, I have to do to the right-hand side as well. So I'll also write plus 9. So what we have here is quantity x plus 3 squared equals 11. Now 11 is not a perfect square. Here's where we're just going to start introducing radicals. We're going to get an answer here we never could have gotten by factoring because there are irrational numbers involved. We will have some expression with radicals. We can put it in our calculator if we like, but we're getting something inherently weird, And this technique allows us to find the solution while factoring would not. So we have that x plus 3 is equal to the square root of 11, or x plus 3 is equal to negative square root of 11. So here we could say x is the square root of 11 minus 3, or x is negative root 11 minus 3. Please notice I still did the plus or minus. Square root of 11 is a number approximately 3.5. Let me get an exact, well, a more exact calculator value for that. Square root of 11 is in the neighborhood of 3.317. So that's a solution, but so is the negative version. So here, this is approximately 0.317. If you take that number and plug it into the original equation, it'll be true, up to rounding. Or x could be approximately negative 6.317. We never would have found those numbers by factoring. Maybe graphing on the calculator would have been an option, but here's a way of finding unusual solutions in a method that's not ridiculously hard. So what did we do? First thing we did is we made sure that we started with plain old x squared. If you have to divide, you have to divide. Then, and we also made sure that we had a number here. So I just had a binomial, two terms, the x squared and something with an x. If there was a third number, I moved it to the other side. We completed the square and we added whatever we needed to add to each side. We factored, and factoring here basically means finding the square. If you're doing this correctly, the factoring is just observation. Oh, I have a perfect square. We take square roots, remembering that we could have positive or negative, and then we solve for x. You can write using the plus minus symbol. I think it's actually better just write them separately. That I said, oh, if something squared is 11, maybe it's the square root of 11, or maybe it's negative square root of 11. You can write the plus minus symbol, but I recommend thinking of these as two answers written separately. All right, so here's another one for you to try. Hit pause and give it a shot. All right, I hope you've done that. So we might notice we're starting with a 3. Right off the bat, I will divide everything by 3. And I will also move that 2 to the other side. Now I can complete the square. Here's negative 4. Half of that is negative 2. Square that is 4. So I'm going to add 4 to each side. X squared minus 4x plus 4 equals negative 2 plus 4. By design, I have a perfect square on the left. On the right, I have the number 2. Not a perfect square, but that's okay. Maybe x minus 2 is the square root of 2. Or maybe x minus 2 is negative square root of 2. This would mean x is square root of 2 plus 2, which is approximately 3.414. Here we would have negative square root of 2 plus 2, which you could write as 2 minus root 2, which is approximately 0.586. Again, exotic numbers we never would have found by factoring. But maybe you're trying to solve something in the real world where, you want to know how long something is and it's not necessarily an integer number of centimeters. This is helpful for getting the number we need. Okay, and just another thing we can do with completing the square, if we're thinking about graphs of parabolas, we can take something that's in standard form and we can write it in vertex form. So let me just walk you through this. If we have this, y equals x squared plus 4x minus 6. Let's just remember vertex form looks like this. It allows us to understand the location and shape of a parabola by noticing where the vertex is. So we actually want to see a perfect square. So what I could do here is I could create a perfect square. I'm going to take this -6 and move it to the side. Here, to create the perfect square, half of 4 is 2. 2 squared is 4. So if I add 4, I've created a perfect square. Well, I can't just add 4. And I don't want to add it to both sides because I'm really trying to think of this as y equals. So I'm going to do a little trick where I add 4 and then immediately subtract 4. So technically I haven't changed the value, I've just changed the appearance. So now I could think, oh, these first 3 terms are quantity x plus 2 squared. And then these last 2, if I combine them, is just the number -10. So this is in vertex form. I have a parabola with its vertex at -2, -10. Thinking about the shifts, we shifted 2 to the left and 10 down. So a very quick picture of this would be something like so. I'm not going to worry about the details. But we were able to change the form to notice properties that were not originally obvious. And just a note here, make sure you always keep the original statement true. So completing the square was our trick, but whatever I did, I immediately undid it so that I didn't actually change the value. Right? I wanted to see a 4, but I didn't want to change anything, so I put a -4 right next to it. Remember that. All right, that is the end of this section.